All right, guys. This is your work for the week of what is it? What are we on here? 420. 420. When did we start this? Yesterday. 424 to 5/1. This week we are going to continue reviewing for our final exam. We have 3 topics we're going to cover in this week's worksheet. Once again, this video is optional. You don't have to watch this video. This is just to help you complete the worksheet. So you're not expected to sit here and watch the entire thing. I would just come around and watch the parts that you need help with. Anyway, so for this week's topics, we're looking at transformations. That's numbers 1 through 9. Second, we'll be reviewing how to graph absolute value functions. That's numbers 10 and 11. And then finally, we will finish with number 12 through 26, which is doing stuff with polynomials like multiplying them, factoring them, etc. So that's pretty much it. The first topic that we're going to look at is transformations. So we'll go ahead and begin there. So transformations are whenever you do something to a function that causes the shape of the graph to change in some way. Now we deal with 3 types of transformations. Translations, which I have in red, expansions and compressions. Those go together. You'll see why in a minute. I've got those in blue. And then there's reflections. So those are our 3 types: translations, expansions, compressions, and reflections. Now those types of transformations can be applied to your function vertically, or they can be applied to your function horizontally. Okay. Now if you want something to be applied to your function vertically, then the changes that you're going to make to your parent function, in this case f of x, your starting function, the changes you make will happen outside the parentheses. So look at all these symbolic representations of the changes that I've made to f of x in the middle column here. First of all, I took f of x and I added a number to it. On this one here, the second one down, I subtract a number. The third one down, I multiply a number. The fourth one down, I multiply by the reciprocal of a number, or you can think of that as dividing by a number also. And then also last one, we make the outside negative. The red ones here result in translations, the blue ones result in expansions or compressions, and then the negative reflects it. So anytime you make a change outside the parentheses, that's going to affect your graph vertically. All right, so let's talk about the translations first. So if you add a number to your function, that will translate the graph up however many spaces that is required to match the number that you added. So for instance here, let's say that I added 2. So we took our function, we added 2 to it. Well, every point on this parabola now is going to go up 2 more spaces. And so the end result would be that your parabola goes up 2 spaces. Well, let's go ahead and take a look at the next one. Let's suppose I subtract 2. That means every point on my curve is going to go down by 2 spaces. So something like this. It just moves the whole shape down. So if you haven't add a number on the outside, it shifts it up, translates it up. If you subtract a number on the outside, it shifts it down. Look at the next one here. So let's assume that a represents a number that is like a whole number, like 2, 3, 4, 5, 6, or something like that. If you multiply your function by a number that's bigger than 1, it's going to vertically expand it by a factor of a. So what that means is it's going to stretch it vertically. But if you divide your function by a factor of a, it's going to compress it or shrink it. I'll go ahead and say shrink. Vertically. Okay, so let's go ahead and take a look at this. So let me do an example. So for the top one there, I multiplied by 2, and that made the parabola look a little bit skinnier. It's like it stretched it vertically. Now, if you want to get technical about this, what it does is it multiplies 2 times, right? 2 times the y values. So any y value gets doubled, right? So for instance, if I pick this point right here where x equals -2, the y equals 4. If I multiply the y by 2, though, I end up with 8. 4 times 2 is 8. So at -2, instead of the y being 4, now it's twice as much. It's 8, and so it's up here. 0 doesn't move because if you multiply a y value of 0 by 2, it stays at 0. So what it ends up doing is it stretches it away from the x-axis however many times farther away than it was originally. Since this dot was on the x-axis, then it doesn't move. Now when you multiply it by a number less than 1, or in other words, you're dividing by 2 instead of multiplying by 2, it cuts all the y values in half, and so it makes your graph look shrunk vertically. Okay. Let's move on to the last one, which is the reflection. So in this case, if there's a number out here, that number is basically a stretch or a compression. But if that number is negative, that does something else. It reflects it across the x-axis. And that's because it makes all the y values become negative. Okay, so like it would be flipped upside down to look something more like this. Okay, and so that is the reflections. And that does it for all the vertical transformations that we could have: translations, expansions, and compressions. Finally, reflections. All of those are outside changes that change your graph vertically in an up and down fashion, but there can also be horizontal transformations. So notice now all the adding or subtracting or multiplying or putting a negative, all those are happening inside the parentheses. They're affecting the x value, which results in horizontal transformation. So if you add a number inside the parentheses, what that ends up doing is it causes your graph to translate or shift left that many spaces. So in this case, it would move it over, right? Like that to the left. Or if you subtract a number inside the parentheses, what it will do is it will shift it over to the right. So adding moves it left, subtracting moves it right. Next, we have compressions and expansions. It's the opposite of what we saw with the verticals. With verticals, if we multiplied our function by a number bigger than 1, it stretched it, it expanded it. But actually, when you multiply inside the parentheses, it compresses it. That's quite interesting. It compresses it that much. So it will actually make it look skinnier. Now, here's the problem. If you squish this thing horizontally, in other words, you're squishing it this way, squeezing it inwards, it makes it look skinnier, right? But I want you guys to remember something, though. A little bit earlier, we talked about the verticals. Vertical expansion looked exactly the same as that almost. It looked like this. But it got that way not by being squished horizontally, but rather by being stretched vertically. So if you stretch something vertically, it almost has a pretty similar effect as compressing it horizontally. Now that kind of creates a little bit of a problem for us in some of the problems we're going to be looking at, because when you're looking at the graph, you're not going to necessarily know right off the bat whether it's a horizontal stretch or horizontal compression or whether it's a vertical stretch. But we'll kind of wade through those confusing waters when we get there. But anyway, if you multiply your x by a number less than 1, or I should say, if you're dividing x by a, that will actually make it wider horizontally. It makes it look wider horizontally. Okay, for our last one here, the reflection across the y-axis is what happens when you put a negative on the inside. Now, this is a bad shape to pick because if you reflect it horizontally, it actually doesn't end up looking different at all. So let me use a different shape to kind of illustrate the point a little bit better. So let's say that, I hate how this thing does that automatically. It does it all the time. All right, so let's say that I have a shape that looks like, let me just make one up real quick here. How about that? Okay, well, if I reflect that across the y-axis, it makes it look like that. Okay, so what it does is it makes all the x values flip. So like over here, you know, whatever point this was, like let's say that was x equals -4. Well, over that same point will fly over here to where x equals +4. So it just makes it look like it's been reflected across the y-axis. Okay, so there's the summary of all the transformations, and that's what you need to know to be able to do numbers 1 through 9. So at this point, I'll just do a couple of problems. Let's go ahead and begin. And once again, these problems are not the problems you're doing, but they look like, you know, they're similar types of questions. So let's go ahead and begin. So as you guys can see, for this particular problem, it's been flipped upside down, and that's a vertical reflection. So we know that there's a vertical reflection, or I guess we could say it's a reflection across it's been reflected across the x-axis. Okay, so looking down here at our options, we know it's not C. All the other ones have reflection across the x-axis, but that's it. But you may notice that that's not quite enough. So let's take a look at what else we can see. Notice that when we reflected it, it would have looked more like this if we just reflected it, but it's actually been shifted down a little bit as well. So not only is it a vertical reflection, but it's also a translation down. It's been shifted downwards. So it's been reflected and translated down. That would be option B. Okay, so that's our goal here, is to find out which one of these descriptions matches what happens in the picture. Let's look at another example here like this. All right, now as you guys can see, this one it looks like it's been like rotated, but we don't have there actually is a transformation for that, but we're not learning that in this class. But how else can we get this blue line here to match the green dotted line? Well, first of all, you would have to reflect the blue line this way, and then you would have to reflect it upside down, right? So it's been reflected both ways. It's been flipped horizontally, and it's been reflected vertically. So that would be option A, a double reflection, reflected horizontally and vertically puts us there, okay? There's been no translations or anything like that. It has not been moved. It's just been reflected. That's it. So that's the end of that one. Let's take a look here. Now, this green line is upside down from the blue one, so there's definitely been a vertical reflection known as a reflection across the x-axis. So we have a reflection across the x-axis. That boils our options down here to C or D. But notice that the starting point for the blue line was at 0, 0, but that starting point on the green line is up here. So to get from here to here, we would have to go over 1 and up 2. So that's two translations, a translation to the right 1 and a translation up 2. So right 1, up 2 is D. So it's been reflected across the x-axis, so it's upside down, and then it's been translated right 1 and then up 2, and that's what gets us there. Okay. Now we're going to switch gears here a little bit, and we're going to look at it a little bit more mathematically rather than verbally. So, but we're still going to think of the verbal aspect of things as we try to solve this. So now as you guys can see, this graph here, the blue line compared to the green line, it looks like they took this parabola and they shifted it over 2 spaces and down 2 spaces. So if you take this blue shape and you shift it over 2, down 2, you get the green one. So to me, it looks like all they've done is 2 translations. So it's been a translation to the right, and it's been a translation also going down. Now, how do you get a translation right symbolically? Well, to get a translation going to the right symbolic, you would have to subtract. And then you're going to have a number here. And to get a translation down, you have to subtract a number out here. So we're looking for an f of x expression where we have a number subtracting the inside and on the outside. So I don't see that on A, so that's not it. I don't see that on B. I don't see that on C. I see that here on D. So D is the one where we've gone right to and down to. Take a look at another example. Now, for this one, it's been shifted up. So definitely see that we have a translation going up a certain amount. Now, on your function, to be able to translate up, that means you have to add a number out here, okay? But you'll also notice the shape is different. It looks wider. Now, there's two ways you can get a shape to look wider. One way you can get it to look wider is by doing a vertical compression. Okay, if you were to squish something vertically, like you put your, take this blue line here and imagine it's like silly putty, and you put your hand up here and down here and you squish those together, then that's going to flatten the blue line out, so it would look a little bit flatter. So that's a vertical compression. So to get a vertical compression, you can have a 1 over A out here. But that's not the only way to get a vertical compression. I'm sorry, a flatter looking line. Another way you can get a flatter looking line is by stretching it horizontally. So if you took this blue line and pulled it left and right with both hands, that would widen it out, wouldn't it? So that's what we call a horizontal expansion. So it's not both of these, it's one or the other. But a way you could get a horizontal expansion is by multiplying your x by a number of some kind. So we have two possibilities. Either it's f of x with a 1 over something on the outside and a plus a number on the outside, or it's an f of x with an a on the inside and a number being added on the outside. So let's look at our options here. We know regardless of which option we need a number on the outside. So this doesn't work, there's no numbers on the outside. This doesn't work, there's no numbers on the outside. So we have two possibilities here. Okay, so that's a little bit unfortunate because these are both the possibilities that we could use. So which one is it? We got a 50-50 guess. So what I'm going to do is I'm going to try to make sure that you guys don't have anything like this on your guys' worksheet, because we didn't talk about how, when you have both possibilities available, how to tell which one it is. I'm going to show you, but you don't have to watch this because I'm not going to put it on on your guys' worksheet. But if you're a math-minded person and you want to know how can you tell, I'll explain it right now. It gets a little bit complicated, so but like I said, you do not need to watch this if you don't want to. Okay, so let me show you. We already know which of these two possibilities it could be. It's either B or C. Okay, so first of all, I'm going to pick a point on the original function. Like, I'm going to pick this point right here, 2, 2. At that point on the blue line, my function is f of x. So that means when x is 2, y is 2. So f of 2 equals 2. So what I'm going to do is I'm going to pick one of these. Let's say I choose this one now, and I'm going to plug 2 in for the g function. Now if I do that, that means I'm going to plug in 2 for the x, just like that. Two times 2 is 4. Now I need to figure out what is f of 4. In other words, if you have on your blue line the original function f of x equals 4, what's the y value? Well, let's look at our blue line. Let's go over where x equals 4 and look at your y value there. What's the y value for that point where x equals 4 on the blue line? Well, the y value is 4. Right? So that means that g of 2 would have to equal 6. So that means that x equals 2, the green line, should be at y equals 6. Is it? And the answer is no. 6 is up here. So it's not that one. So we already know it has to be C. But just to kind of demonstrate this process again, I'll go through this one for you. But just to show you that it works. But you don't really need to because we already know what the answer is, right? But let's do it again here. So let's take this function, g of x equals 1/2 times f of x plus 2, and we're going to plug in 2 again. So let's see what this one gives us. Now we already know that f of 2 equals 2. So I'll just put 2 here. F of 2 becomes just 2. Half of 2 is 1. Let me erase that. So if I take this 1/2 times 2, I end up with 1. And so g of 2 should come out to equal 3. Now let's see. At x equals 2, is the green line at 3? And the answer is yes. So that's our answer. So this is the one that works. Okay. But once again, I'm not going to give you guys something that specific. And you guys, I'll try not to include one where you have to make that kind of a decision on your worksheet. But just thought I'd go through it with you. But let's go ahead and move on to our last one here. So for this one, you could tell it's been reflected across the y-axis. All right. Also, even though it's been reflected across the y-axis, it's also been shifted one space to the left, because usually the starting point is here, but it got shifted over one to the left. So we have a translation to the left. Now usually, for your function, if you want to be reflected across the y-axis, you need a negative in front of your x. And if you want it to be translated to the left, then what you need is you need a number to be added to your function. Okay? So we're looking for a number where a number is being added to my x, but there's a negative outside in front of the x there. And which one of these matches that? It would be option C. Okay? So that's another perspective on the same question. Let's look at the same question yet another way. This one's pretty simple. We're just going from the symbolic representation to the verbal. Okay, so let's go ahead and see if we can do a couple of these now. Let's assume that my original function was f of x equals x. Okay, all you have to do is really look at this part. It looks like my x is being multiplied by a number on the outside, and it also looks like my x is being subtracted by a number on the inside. So why do I say they're both on the inside? Because they're all in parentheses, right? So we have a multiplication happening inside the parentheses, and we also have a subtraction happening inside the parentheses. When you have a multiplication of a number bigger than 1 on the inside of the parentheses, that makes for a vertical, no, I'm sorry, not vertical. I recant. That makes for a horizontal, because it's inside, a horizontal compression. And also, we're subtracting a number from the x on the inside of the parentheses. When that happens, that's a horizontal translation to the right. So which one of these descriptions has a horizontal compression and a translation to the right? That would be option B. Take a look at another one here. So for this one, I've got a number multiplying the x, but notice that that number is less than 1. When that happens, when you multiply by a number less than 1, that is a horizontal expansion. And then when you add a number to your x inside the parentheses, that is a translation to the left. So we're looking for a horizontal expansion and a translation to the left. Let's see. That would be option C. One more problem before we move on to our last one here. So for this one, what's going on here? Notice that we have two differences to get from here to here. We have a 3 on the top. What's up with that? And we also have a negative here. All right, so let me help you guys understand this a little bit. the parentheses aren't there. So where are the parentheses, right? How do you know if this is an inside change or an outside change if there's no parentheses? Well, the parentheses are always around the x. So in this case, since we have the 3 on the top, that's an outside change. We can get from here to having the 3 on the top if we multiply by 3. So what I did was we multiplied by 3. And when you multiply by a number bigger than 1, what that is a vertical expansion. We took 1 over x, right? My parentheses are down here, and I multiplied on the outside by 3 to get this, right? So that when you multiply on the outside by a number bigger than 1, that's a vertical expansion. Notice the negative is also out here. It's not inside the parentheses. So that's also a vertical thing. So that is a reflection across the x-axis. So we're looking for a vertical expansion and a reflection across the x-axis. Let's see. There it is, part B. Expansion vertically and reflection across the x-axis. And that's transformations for you. Okay? We're going to move on to the next part of our discussion, which is how to graph absolute value functions. Okay, so let's talk about how to graph absolute value functions really quick. So absolute value functions look like a V shape. Okay, now the format that we need to be familiar with is the following. All right, so first of all, this number here makes the x value of our vertex. And this number here makes the y value. But you have to understand that for the x value, it is going to be the opposite sign. So notice this says negative h, but down here it's a positive h. In the same way, if it was a positive h, you would have a negative down here. That does not happen with the k. All right, now as for this guy here, that's kind of like our slope. Okay, so but with absolute value functions, the slope is a little bit different than it is on just a straight line. For the absolute value function, you're going to rise, and when you run to the left and to the right. That way, you end up with 2 dots, one on the left and one on the right, and when you connect your dots, you get that V shape that we're trying to go for. So that's how we do absolute value function graphing. So let's go ahead and do that with this real quick. So as you can see, my h is 4, but it's negative, right? So my vertex is going to be positive 4 because you change the sign. For this one, the k, it's a positive 4 and we don't change the sign. So this is my vertex, 4, 4. Notice my slope. So we have a slope of negative 2, but we'll get to that in a second. Let's start by graphing the vertex really quick. So I'm going to go over 4 and up 4. And that's where my vertex is. Now my slope is negative 2. So let's think of that as negative 2 over 1. That means I'm going to go down 2, and I'm going to go to the left one, and I'm also going to go to the right one and put a dot at each side of that. So if I went down 2 and left 1 from the vertex, that would put me there. And then starting from the vertex again, if I go down 2 and right 1, that would put me there. And there's my V shape. Okay, so we have to find the shape that matches that, and as you guys can see, that's option B. So that's graphing absolute value functions. And this is just to demonstrate to you guys what to do if you're missing numbers. So instead of doing the problem, I'll just remind you of some basic facts here for this one. If you're missing the A, then that means A equals 1. If you're missing either H and or K, that means they equal 0. Okay, so if you're missing A, that's 1. If you're missing H or K, there's 0. The reason for that is because if you have something like this, y equals the absolute value of x, how can you put a number here without actually changing it? Well, it would have to be a 1 because 1 times anything just leaves it the same, right? Because it's multiplication. But if you were missing a number over here, what can you add so it doesn't change it? Well, if you want to add a number to something without changing anything, you would add 0. So the multiplication identity is 1. The additive identity is 0. So if you're missing the A, it's 1. If you're missing the H or the K, I'm sorry, if you're missing the A, it's 1. And if you're missing the H or K, those will be 0. All right, so that is graphing absolute value functions. And now we get to move on to our last topic, which is polynomials. We're going to talk about a couple of different topics with polynomials. We're going to talk first about adding and subtracting polynomials. That'll be our first topic, and that's what the first problem is you see here on the left. After we talk about adding and subtracting, we'll move into multiplication. And then finally, after we talk about multiplication, we'll move into our last topic for polynomials, which is factoring. And that will be the end of our work for this week. So let's go ahead and begin talking about adding. Now, when it comes to adding polynomials, basically you just need to combine their like terms. Now, personally, I like to put the numbers, and so does the software that I'm using, as you can see. We like to put the numbers that have the biggest powers in the front. So I'm going to start with this x to the 4th. Next to it, I'm going to put 7x squared. And then after that, I'll put a minus 2, because that one doesn't have any x's at all. Now, we're adding to that polynomial this expression. And as I do it, we want to line up the like terms. So negative 8x to the 4th would go underneath of this positive x to the 4th here. 3x squared would be next. And then finally, we have a negative 3. Now, remember, when you're missing a number that would be being multiplied, that's a 1, right? So there's a 1 there. And basically, all we're doing is we're combining these together. So what does a negative 2 and a negative 3 make? Well, if you combine those, that makes a negative 5. What does a positive 7x squared and a positive 3x squared make? Well, when you're adding like terms, you only add the coefficients, and the variable and exponent don't change. So 7 and 3 make 10, so now we've got 10x squared. All right, and then finally we have this last one. We have a positive 1 and a negative 8. Put those together, we end up with a negative 7, and once again, you don't change the variable or power when you're just combining like terms. So there's your final answer. So just combine the like terms as they are, and that would be option B. All right, moving on to another one. Now, something a little bit different happens, though, whenever you're subtracting instead of adding. Notice here we're subtracting. All right, so when you're subtracting, this minus is going to get distributed to each one of these terms, and it's going to change their sign. So what I'm going to do is I'm going to rewrite this whole expression really quick. And now all of these things here, their sign is going to change. So instead of 5r, it's going to become minus 5r. Instead of minus 4r cubed, it's going to become plus 4r cubed, and so on. And now what I'm going to do is I'm going to start lining up the terms that match again, right? So I'm going to go ahead and take this 5r squared here, and I'm going to move it right over here underneath of this r to the 4th, because they both have the same power. And then I'm going to take this guy and I'm going to put it, he doesn't match anybody, so he's going to stay, actually. There's no other numbers that have an r to the 3rd power. And then we're going to look at this guy, negative 5r. I'm going to take him and I'm going to move him on here underneath of this guy. Being a little bit messier this time, I didn't organize them in order, but you don't have to do that first. You can do that last, so I'll just do it last. But anyway, so as you guys can see, the 7r squared has nothing to combine with, so it's just going to stay the same. But I have a positive 3 and a negative 5. That makes a negative 2r. I have a positive 1 and a positive 5. That makes a positive 6r. This is gone, so we don't care about that anymore. But this guy didn't have anybody to combine with, so we'll just bring it down as is. And then this one's gone also. We combined it with something else. Here's our answer. And like I said, we do prefer to have them lined up from highest exponent to lowest. So if we did that, we would have 6r to the 4th plus 4r cubed plus 7r squared minus 2r. Way to write our answer, and that's how they'll have it up here. And the only one that matches that would end up being this guy right here. So that's adding and subtracting polynomials. Let's move on to multiplying polynomials. When you multiply polynomials, you're usually going to end up using the box method. So without any further ado, let's jump into it. So we have 5x minus 2. Oops, I did not write that correctly. Minus 2. And then 8x plus 1. Okay, so the first polynomial in parentheses you can put on the top. The second one you put down the side. It really doesn't matter which one goes where. It's going to work out the same either way. But now, understand we're multiplying now. So that's a game changer. Where this is different than adding. When you multiply polynomials, you multiply the coefficients together. So 8 and 5. 8 times 5 makes 40, right? But when you multiply variables, x times x gives you x squared. What you end up doing is adding the exponents together. Multiply variables. So this variable has an exponent of 1. This variable has an exponent of 1. So when you multiply those variables together, you add the exponents of 1 and 1, and you get 2. All right, now let's continue that here. So 8 times negative 2 is negative 16. And the x has nothing to multiply with up here, so we just leave it as x. 1 times anything is just going to end up staying the same, right? And 1 times negative 2 is negative 2. So we end up with 4 answers, right? But usually, 2 of those are going to end up being the same. So I've got a 40x squared if I start by writing my biggest number. I've got a negative 16x. And I also have a positive 5x. I'm going to line those up because those are like terms. And then we have our minus 2. And if we go ahead and just add our like terms together there, negative 16 and 5 combine together to make negative 11x. And then bring down the minus 2. And we see that our answer is part D. Okay, next one we'll look at here. This one is a binomial by a trinomial. Binomial has 2 terms. Trinomial has 3. When that happens, you need to use a box that's a rectangle. You need one side to be 3 spaces long and the other side to be 2 spaces long. So we have 4p squared minus 2p plus 7. And then for the other one, the binomial, I'll put that down the side here as 4p minus 2. And once again, you just multiply to fill in your box. So we have 4 times 4 is 16. And p to the first power times p to the second power is p to the third power. And so on. 4p times negative 2p is going to be negative 8p squared. 4p times 7p is going to be 28p. Negative 2 times 4p squared is going to be negative 8p squared. Negative 2 times negative 2p is going to be positive 4 because the negatives canceled. And negative 2 times 7 is 14. And then once again, we just take out our numbers, putting them in order. So 16p cubed would come first because that's the biggest power. Then we have the squares, minus 8p squared. And we have another 8p squared there. You'll notice a lot of times that the ones that go together are diagonal from each other. The next ones that we have are the p's, so 28p and 4p go together, those two. Once again, diagonal from each other. And then finally 14. Final answer. Combining the like terms, we end up with the following. And that would give option D, it looks like. So that's how you multiply a binomial and a trinomial. Now, notice the directions for the next two are find the product using shortcuts. Okay. Now, whenever you have two binomials that are being multiplied, where they're the same exact numbers but opposite signs in the middle, all you have to do is multiply the first terms together, multiply the last terms together, and just know that middle sign is always going to be a negative, because when you do a positive times a negative, you get a negative. Okay, so you don't have to do the box. You could do the box and it will work, but this is a shortcut. So in this case, if you did 8a times 8a, you would get 64a squared. And if you did 5 times negative 5, you get minus 25. So that would be option. Shortcuts are nice. Box method works, but shortcuts are nice. Now here's another one. If you have a binomial that is being squared, which is really just another way of saying that you're multiplying that binomial by itself, once again, you could do the box method, but there's a shortcut. The shortcut works like this. You do the first terms multiplied together, and you do the last terms multiplied together. Nothing new there, but there is something different that happens in the middle. In the middle, you multiply the two inside numbers together, a times b, and you double it. Okay, so that is how this one works. It's a little bit of a different shortcut. So for 4r plus 1 squared, let's think of that as 4r plus 1 times 4r plus 1, right? So if I multiply the first terms together, I get 16r to the second power. If I multiply the last terms together, I get 1. If I multiply these two together, 4r times 1, I get 4r, but I double it to get 8r. And there's our final answer. It's a little bit faster than the box method. But once again, that only happens in those special situations where you're multiplying a binomial by itself, or squaring it, or if you're multiplying it by itself but with opposite signs. Last topic for polynomials is factoring, so we'll move on to that next. All right, so we're going to talk about 3 factoring strategies. First one is the GCF method. Okay, that's where you divide out something that all the terms have in common. After that, we'll talk about how to factor something with 2 terms. It may be a difference of squares. And we'll also talk about if something has 3 terms, or if it has 4 terms. Whether it has 3 or 4 terms, then we use the box method. And that's it. So GCF, and then if it has 2 terms, difference of squares. If it has 3 or 4, we use the box method. We're just going to do one strategy at a time, and at the end we'll kind of look at problems that kind of put the stuff together all at once. Okay, so let's go ahead and take a look at number 18. The first one says factor the common factor out of each expression. That just means take out the GCF. So we have 10x to the 5th plus 20x cubed plus 30. So we're going to put some parentheses here, and each one of those 3 numbers are going to change because I'm going to divide something out of them if I can. So now let's begin. Let's focus on the coefficients first, 10, 20, and 30. What can you divide out of 10, 20, and 30? Well, there's lots of different answers you can give, but you want to divide out the biggest thing you can. And it turns out the biggest number that divides into all 3 of those is 10. So we're going to take out a 10. So if I divide 10 by 10, I get 1. If I divide 20 by 10, I get 2. If I divide 30 by 10, I get 3. Now let's look at the variables. What can you divide out of all of these x's that they could all be divided by, right? Well, this one can be divided by 5x's. This one can be divided by 3x's, and this one can only be divided by 1. Now you're only allowed to divide out what they can all be divided by. So the only thing you could divide by is x to the 1st power, since that's all this one can afford to be divided by. So if you divide x to the 5th by x to the 1, you subtract the exponents and you're left with 4. If you divide x to the 3rd by x to the 1, you subtract 3 and 1 and you get 2. And if you divide this one by x, you're left with 1. So anything divided by itself is just 1. There is no more x's there. 1 minus 1 is 0, right? But that means the power is 0, and any number to the 0 power equals 1. So x divided by x equals 1. And so there's your final answer. We have 10 to the x times x to the fourth plus 2x squared plus 3. Which one looks like it's option C? So that's how you take out a GCF. Now, when you are dealing with a polynomial, now notice it's not asking us to take out a GCF, and if you look at it, there's no GCF anyway. This is a 1, 7, and a 6. You can't take the greatest common factor out. And this last number here doesn't have any x, so you can't take the x's out either. There's no GCF to take out. So what do? Well, this one has 3 terms, and when there's 3 terms, we use the box method. Now, these are the hardest ones to factor because you're dealing with a lot of unknown stuff here. What we do know is that we want to find 2 binomials that will multiply together to make this. We just don't know what those binomials are right now, and that's our job, is we want to figure out what those binomials are. We know that the binomials, when they multiply together, the first 2 terms should make x squared. So x squared goes here. So we're looking for something times something that makes x squared. We also know that the last 2 terms of our binomials would multiply together to make this 6. So the 6 goes down here. Now the 7 is the tricky part, because the 7 is actually 2 numbers that were put together. It's these 2. These 2 numbers would be put together to make 7, but we don't know what those are right now. But there's a lot of ways you could split 7 up. So we don't know which, is it 3 and 4? Is it 2 and 5? We don't know. So this is all we have to work on. So whenever you're trying to factor a trinomial using the box method, first thing you do is you put the first term in the top left, you put the last term in the bottom right. Then the next thing you're going to do is you're going to find what 2 numbers can multiply together to make x squared. Well, that would be x times x, right? Only one possibility. We know it's got to be x and x here, because those multiply together to make x squared. The next thing we're going to do is we're going to look for 2 things that multiply together to make 6. Now, you could think of 2 and 3. Let's try it. But 2 times 3 does make 6, right? Let's go ahead and fill in our box and see if this works. X times 2 is 2x, and 3 times x is 3x. We know we're right if these 2 numbers add together to make the middle number that we want, -7. Does 3 plus 2 make -7? The answer is no. So we've made a boo-boo. Now there's 2 things you could do. You could try changing the signs. So for instance, -2 and -3. That also makes +6, doesn't it? But all that's going to do is change the signs in here, and still when you add a -2 and -3, you still don't get -7. So changing the signs didn't work. Now the other thing you could try doing is switching the numbers around. So instead of putting the 2 up here and 3 down here, you could put the 3 here and the 2 here. Now I'm going to save us the trouble. I'm just telling you what possibilities there are, but in this case that's not going to work either. So so far there's 2 things you can try if it doesn't work. Change the signs or switch the numbers. If both of those fail, then what you need is completely different numbers. So what else can multiply together to make 6 other than 2 and 3? Well, the answer is 6 and 1. So we know that's got to work because there's no other way to get 6. So let's try a +6 and a +1 first. So x times 6 is 6x, and 1 times x is 1x. Well, this is really cool because 6 and 1 does make 7, but the problem is it's not -7. It would be, though, if they were both negative. So if I just go back and change the 6 and the 1 here to being negatives, we're in business. So now I see that this thing factors into x minus 6 and x minus 1. So basically, first step, first term goes in the top left, last term goes in the bottom right. Find 2 numbers that multiply to make the top left number, and then find 2 numbers that multiply to make the bottom right number. If you fill in your box and it doesn't give you the middle, then you have 3 things that you need to try doing before you give up. One is change the signs. The other is switch the numbers around. The third thing is change the number values completely. If all those things fail, then maybe it's just not factorable. That's possible. But I'm pretty sure most of the problems I'm giving you will be factorable problems. All right, so we get to do it again here, just to kind of practice a little bit more. So step one, let's make our box. Step one is to put the first term in the top left and the last term in the bottom right. The next step is to find two numbers that multiply to make the top. 2b times b would give us 2b squared. And then the next thing we do is find two numbers that multiply them together and make 10. I like 2 and 5. Let's try that. Now let's multiply to fill in our box and see what we get. 4b and 5b. 4 and 5 are not going to add up to make 19. So I've got some bad things here. Now if I change the signs, that's not going to work either, because all that's going to do is change from being a negative 9. It's going to change from being a 5 plus 4 to a negative 5 minus 4, which changes the sign. It doesn't change the value. I need a 19. Maybe if I switch the numbers around, though. Let's try that. So let's put the 2 down here and the 5 up here. 2 times 5 is going to give me 10b. And then change this also. 2 times b is going to give me 2b. 10 and 2, the most that can give me is 12. So we're still not there. So since changing the signs and switching the numbers locations around didn't work, that means it's not going to be 5 and 2. I have to try two completely different numbers. How about 10 and 1? Let's see if that works. Oops. All right, 2 times 10 will be 20b, and 1 times b will be 1b. All right, well, 20 and 1 actually can combine together and make negative 19, but that's only going to happen if the 20 is negative and the 1's positive. So that means the 10 is negative and the 1's positive. Let's make sure this all works. 2b times b is 2b squared. 2b times negative 10 is negative 20. 1 times b is 1b. And 1 times negative 10 is negative 10. And these do add up to make negative 19. So we're in business. The answer is b minus 10 multiplied by 2b plus 1. So that is the factoring strategy for trinomials. That's interesting. I'll come back to that in a second. Looks like I just made a third one. I think I'm going to leave it, though. I'm not going to bother with doing a third example. Now, for this one here, it's a binomial. Once again, does it have any greatest common factors involved? No. You can't divide 4 and 25 by anything. And also, this one doesn't have any variables to give up. So there's no GCF. All right, so here's this method when you have two terms is you're going to apply the difference of squares method. I'm going to abbreviate that. The difference of squares method means that you're going to take the square root of that. What times what? What times itself makes 4n squared? Well, that would be 2n. And you're going to write that twice. Then you're going to take the square root of 25. That's easy. That's 5. You make 1 plus, you make 1 a minus. You got to be kind of careful here. This only works if this is a minus. If you don't have a minus here, you can't do this strategy. So be very careful. If I gave you this, then that might be me just trying to be mean and trick you. The answer would be it's not factorable, because that's not a difference. Difference means subtraction. That's not a difference of squares. That's a sum of squares. But a difference of squares factors like this. So the answer is 2n plus 5 and 2n minus 5. Do another one like that. So in this case, we have 16k to the 4th power minus 9. So square root that. That's 4k squared. Square root the 9. That's 3. 1's plus, 1's minus. Option. Okay, last one we'll look at here is 4-term polynomials. So there's 4 terms in here. This actually isn't the last one. We had a little bit more to talk about in a second. We'll get to that. But once again, there's going to be no GCF in the first few examples. The GCFs come later. So when there's 4 terms, we're back to the box method. The box method is a little bit easier for these ones, in my opinion. So first term goes in the top left. The reason I think it's easier is because there's not as much guessing going on. You can actually just get the answer right. The last term goes in the bottom right. The other two terms, it doesn't really matter where you put them. Just put them in there somewhere. Now what we're going to do is we're going to take out the greatest common factor here. So you're going to do it for these two terms, and you're going to put your answer here. So what's the greatest factor for these two terms? Well, 15 and 21 can both be divided by 3. And this one has 3 m's to give up, and this one has 2 m's to give up. So I can take out at least 2 m's. You're going to repeat that with the bottom row. What's the biggest thing that goes into 25m and 35? 5 goes into both of those. But you can't take out any variables because this last one doesn't have a variable. Okay. Now we're going to repeat that process, but this time we're going to be going vertically. So let's look at these two terms. What is the greatest common factor for these two terms? For 15 and 25, the biggest thing you take out is 5. And for m cubed and m to the first, the most you could take out is m. Repeat that process for the last column here. The biggest thing you could take out of 21 and 35 is 7, but you can't take out any variables. Okay, and that does it. You've got your answer. It's 5m plus 7 and 3m squared plus 5. So that would be this guy here, option. Now for the last two problems here on this worksheet, these are just multi-step problems. So on these ones, the first thing you're going to do is you always start by looking for a greatest common factor first. So let's begin. There is a greatest common factor this time. What can you divide out of 2, 12, and 14? The answer is 2. If you divide all three of those by 2, you end up with the following. Now, we're still not done though. This thing on the inside has 3 terms. So for that, I would apply the box method. And when I'm all done, I'm going to put my answer down here. Okay? So first term of the trinomial goes here, last term of the trinomial goes here. Two things that multiply together make r squared, or r and r. Two things to multiply together make 7, or 7 and 1. Now, let's see here. R times 7 is 7r, and 1 times r is 1r. 1 and 7 can add together to make 6 if the 1 is negative, which is cool. That's what we want. So we have a positive 7 and a negative 1. So we have r minus 1 and r plus 7, which would be this guy here. This is a multi-step problem. GCF first and then box method. Let's take a look at the next one and our last one. Another multi-step problem. Let's start by looking for our GCF. Both of those can be divided by 2, so I'm going to take a 2 out, which will make 25n to the 4th minus 16. Now after that, this piece here has 2 terms, so it may be a difference of squares. So we're going to square root that first term, which will give me 5n squared. And then we're going to square root the last term, which is 4. And there's our final answer. Sometimes even past this you can keep going. Like for now I know I'm done for sure. But what if this, instead of being a 5, what if this was like a 9? Well, you could take the square root again on this guy and split it up more. This one would definitely be done because it's a plus, but this one could possibly have been another difference of squares, but because of the 5, you can't take the square root of 5, so we don't go any further than that. So the answer here would be D. And that does it. So that's the end of our review for this week.